Now let's see some examples of using dynamic memory allocation. In a previous video, I introduced you to dynamic memory allocation and we created a one-dimensional array. Now let's look at the idea of creating a two-dimensional array. So up till now, we would do something like this. Int d square bracket. I could leave this empty if I wanted to, but we'll be explicit. 2, 3. I have to have the 3. And then curly brackets, 1, 2, 3, 4, 5, 6, curly bracket, semicolon. In a video in which I talked about arrays, I pointed out that the way this is stored is really as one continuous line. So the numbers are stored for this the same exact way they would be as if I'd created this. Int x6 equal curly brackets 1, 2, 3, 4, 5, 6, close curly brackets. In memory, these are stored identically for C programs. Wouldn't necessarily be the same for other programs, but it is for C. It's this part right here that imposes the structure on it that allows me to access elements using 2 dimensions. Because here, if I want to get to the 4, I write x sub 0, 1, 2, 3. And to get to the 4, over here, I write d row 0, row 1, column 0, right there. Once again, this imposes that structure on it, not necessarily the curly brackets, whatever, because in memory they're stored the same. Another thing to remember about arrays like this is that even though I see a two-dimensional construct, in terms of how the pointer arithmetic that this represents behind the scenes or gets converted into treats this really as an array of arrays. So D consists of 2 one-dimensional arrays, where each of those one-dimensional arrays contains 3 ints, since that's what we have here. It's that idea of an array of arrays which is what I will need to use if I'm going to construct this using dynamic memory allocation. And what I mean by that is that the first row really will be stored in its own memory. And the second row really will be stored in its own memory. And then I'll need to store the addresses from the 2 calls to malloc. So how do we do this? The mistake to make would be thinking at the beginning about ultimately I need to store an address and trying to remember, well, how many stars do I use if I'm using a two-dimensional array? Here's the way I think about it. I start on the inside and work my way back out. So the first row consists of an int, an int, and an int. And so if I call malloc to create memory that will let me have 3 ints, then what's going to give me back is something that I should treat as the address of an int. So I'm going to get the address to where this first int will be. And having a variable of this type is what causes the pointer arithmetic to move to the appropriate things. Without that, malloc doesn't actually know how I'm going to use this. It's the variable that I store this in that allows me to move from int to int. And so then the second row will be the same thing. Int, 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 and int star. So now I need to store the 2 int stars, right? So I want an array for that. And if I wanted to produce that dynamically, I draw it like this. If I want to store this dynamically, well then this call to malloc will return an address. And what's its type? Well, this is int star, so I need something that can store the address of an int star, which means int star star. And this would be variable D. So this is the initial variable I'll create, int star star D. And then I'll call malloc and do it in the reverse order. Because if I create this first, then I still need some place to store the address that malloc returns. So I might as well do this first. So when I do this, D equals malloc, and we'd fill it in. That's going to give me what I drew like this. And then this part right here is D sub 0, and this is D sub 1. And I'll use those to then store the addresses for the individual ints. So let's do that. So int star star d, and I'll probably need a variable I for printing or something here in a minute. So d is equal to malloc. And what do we need? I'm going to need 2 times size of int star. There's an int star, there's an int star, and there's 2 of those. So I need the amount of memory this takes, which on my computer would be 2 times 8, because each of these are 8 byte addresses. So it's really 16 bytes, but I don't want to hard code that. So it'd be 2 times size of an int. So now I have a block of memory that can store those addresses that I'm going to get from malloc next. So now I can have d sub 0 is equal to malloc. I'm going to store 3 ints. So it's 3 times size of an int. Do the same thing for d sub 1. At this point, I have my 2-dimensional construct, but it doesn't currently contain any values. So let's put some values into it. I is equal to 0, I is less than 3, I plus plus. And we can do this a couple different ways. I'm going to have this counter here with an initial value of 1. And we'll need a variable k. K is equal to 0, so this really is 2. Sorry, because there's 2 rows. I'm making this up literally on the fly. So I'm having to think through what I really should do. K is less than 3. K plus plus. And this will be d sub I sub k is equal to counter. So where do I update the counter at? Well, every time I do something here, I need to update it. So it's really here. So to start off with 1, I'll put 1 here, increment this one, increment k, it goes 2, goes 3, then k gets too big for this, so it comes up here, increments this, comes down here again. We still have the last value of counter, which should be up to 4, so I just keep incrementing that. And then if we want to print, I'll do something similar, except now I don't want the counter. There's my array. So once again, what's the process of creating this? And then if I want it free, let's not forget that, but over here, let me put a comment here so I don't forget. Create the place to store the addresses for these 2 arrays, then create those arrays, and then however you choose to populate it's based upon the problem. So what order do I free? Well, if I start with free D, I certainly can do that. But remember, D is storing the address for these 2 blocks of memory. So if I do this first, now I don't know what was stored in D0 and D1. So I've created a memory leak. There's blocks of memory that I can never free up now. So instead, I want to do it basically in reverse order. Not completely reverse, because these are independent of each other. So I could D sub 1 first if I want to. It doesn't matter on that. But nonetheless, I want to free both of these. And really, if this was a larger array, I really would have done this. Oops. like that. So if there were 1,000 rows, I certainly don't want to hard code each call to free. I just call this the same number of times as our rows. And it works. So that's creating a two-dimensional array. Now let's talk about a one-dimensional array, or excuse me, let's talk about strings. So we saw up till now, if I want an array of strings, it really was an array of string literals, so I did something like this. In fact, let's do this because I'm going to have several functions here. We'll just put them all here. Void, a, void. So I have like char, star, s, equal, I need square brackets. And we'll call this x. We can do s. And just make it readable. I'm going to say cat, dog, bat, or rat. Let's test that out. Oops. Expected. Left that off. So we did this. This is certainly fine for many things. But what's the downside of this? This is probably the most restrictive way that I can create an array of strings. Because this right here has a fixed size. Even though I didn't put a number here, it's going to default to counting how many addresses did I store, and there's 3, so I can only store 3 addresses. I can change the addresses, so I could always come in here and do this if I want to. S sub 1 is equal elephant, which means now I just lost the address for dog. It's still stored in memory somewhere, I just don't know where. So there's my elephant. So I can do that. But I can't change how many addresses I store, and then each of these is also stored as a string literal, so I can't technically change any of these. What I just did with elephant was to store a different address. I didn't replace this spot in memory with something else. So even if you said, well, what about replacing the C with B to get bat? It still takes them out of memory. Well, that's true, but with string literals, I should assume that I can't change them, because I think the standard technically says it's undefined behavior, but string literals are typically stored in a spot in memory that you don't have write access to, so I can't change this. All right? So let's move to the next level. We'll create a function B. And of course I'm hard coding lots of things because we don't have an actual application. So what could we do now? Well, I could do this. I could say, okay, 3. And I could do this. S sub 0 is equal to malloc. And then really, in normal circumstances, I'd want to say how many things to store plus the terminating null times the size of the objects. But I know that each array of characters consists of the number of characters times 1. So I'm just going to hard code this. So I'm going to have 6 in here. So it means I can store up to 5 letters. Let's do this, string copy, S sub 0, snake, so that's 1, that's 2, we'll make this shark, It's also 5 letters plus terminate null. And tiger. Oops. Got to change this to B since I cut and pasted that. And there's my second set of strings. So what's the difference between this and the first one? Well, this is still hard-coded, but now these are flexible. So if I wanted to free this up, and really I should free these, but I'm not going to go to the trouble. But if I wanted to, I could always come along later and do something like this. We'll pretend that this is later in the program and I realize I need to change something. So I could say free S sub 0, which frees this block of memory. And then I could say S sub 0 is equal to malloc. And let's say 20, since that'd be big enough to store elephant. So there's my elephant. So is that really the same thing I did on the first one? Well, no, because in the first one, I wasn't able to free up the string literals. Here, I freed up the memory storing snake, got a new block of memory that was bigger, and then put something into that. And I also I could free this up and now get a smaller block of memory and put something in if I want to. So it has more flexibility than the first version, but it still is hard-coded here. So now let's look at a third version. That's the most flexible of the 3 that we'll look at. So this is really an array of arrays. So I need 2 stars. So if you think back to what I did before, when I was talking about this right here, now just think char, char, char. So this would be char star. This is char star, and there's the third one, char star. So this needs to be char star star. So it's the same idea. So S is equal to malloc 3 times size of char star. And of course, I've hard-coded 3, but in a real application, you might determine this on the fly, so you don't know at the time you're writing the code necessarily what that number is. And now we'll change these to these. 8, 8, 8. I don't need this anymore. And we'll change these to dolphin, giraffe, leopard. So there's the third way of creating an array of strings. I would call each of these an array of strings. It's just that this is the most restrictive, and the last one we did gives you the most freedom. And of course here, just like up here, if we were to add it, this would really be, if I fix this, then I'd say free S sub 0 and for this one, it's going to be similar to what we did with this array of ints. So I do this and then free S, because the block of memory that stores the address of the strings, oops, where was that? Sorry, I put this in the wrong one. It's right here. So this block of memory, it stores the 3 string addresses. It's stored in S, and then these are the arrays of characters, or the block of memory for storing a null terminated array of characters. So let's make sure it still works. Oops. And what did I do wrong? Oh, because I hard-coded 0, sorry. And I probably did the same thing up here. So why is that generating an error? Well, The first time I free up S sub 0, it's fine because it contains a valid address. But each additional time it was an error because it no longer has a valid address. Or, I mean, it still contains that address, but it no longer is connected to a block of dynamically allocated memory. That was the mistake. And so see, now it works. Let's look at a third example. Or excuse me, let's look at a different example that has to do with functions and passing pointers and stuff. So let's say that what I want to do was have a function that will create a one-dimensional array for me, and then its purpose is to do that for the calling location. So one way to do it would be this. Int star, say P, and P is equal to function A, and then when we get it, we'll print the contents for I is equal to 0, I is less than 5, I plus plus. And P sub I. So let's create that function. So we say the return type is int star, because that matches what P is, because that's what we're assigning to. So int star function A, and then we don't give it anything. And actually we could. Let's do this. Int n. We'll change this to say int size equals the 5. Size. Just to show that I don't have to hard code everything. And so I might do this. Int star, or we'll go ahead and do the I. Int star D equals malloc. I can do all this at the same time, since I'm not going to create additional variables after this, I don't think. So it'll be n times size of an int. And this now is called n down here. So d sub I is equal to, we'll just make it that 0 through 4 is what this will actually be. Return d. And ultimately I would need to free, and though I could do this after the fact, I could say free p. So let's see if that works first of all. So what did I do? I call function A, give it the size of the array I want. It comes in here, we're calling it n here. So this is malloc n times the size of an int. So malloc actually got 5 times 4 is equal to 20. And so D is the address to a block of 20 bytes, but because it's a size int star, then the pointer arithmetic knows that when I write this, how to jump 4 bytes at a time to get to the next int. So I've created this block of memory using malloc. If you haven't seen my previous video, which was we discussed the heap and the stack, this is probably created in the heap, and so it exists even when the function itself ends. So when I return the address, I can assign it to P. Now D itself no longer exists, but I didn't care about D. I cared about the address stored in D. And so now I've returned it, saved it in P. I can go through using P sub I. And so it's no different than if I had just said P equals malloc n times size of an int down here. It works exactly the same way. And then ultimately I free up the block of memory that's stored at the address that's in P and free P. So this is one way to do it, and I do this a lot. But what if instead we weren't really able to, or chose not to return the address, but instead I wanted to use a pointer to return the address? Now you might be tempted to do this. We're about to break this because this won't work. Or sorry, yeah, P. So we give it P. Well, P's int star. And then that means up here we would say int star D. Fix that. But this is wrong. And it tells me that's wrong. One, it doesn't know what n is because I got rid of that. So let's do this. So I'm really breaking several things. But let me go ahead and fix this because I'm going to use it here in a minute when I fix the rest of it. That's not the problem I was trying to generate. It's this I was trying to generate. Assignment makes integer from pointer without a cast. So what did I just pass in down here when I wrote P? Well, first of all, P is an uninitialized variable. So I assume that the block of memory that it represents contains garbage. But even if I knew what it represented, the problem is I don't want to pass the content of P. What I want to do is, instead of returning D, because here's what I'm really trying to do. I'm trying to create the block of memory here and somehow get this address that's stored in D back to P so P can use it without returning it. That's the problem. So let's see how I really should do this. But let's just go ahead and compile this again. But once again, it's not going to work correctly. So it's still the same error. This is wrong. So let's fix it. So let's think about what just happened there. So in main, I said int star P, and then we called our function A, and I gave it P in size, but that's not relevant to what I'm talking about now. But when I create this, I got a block in memory. I call it P. It has some address. Let's say it's BF00, and then there's garbage here. And what I'm trying to do is that in function A, I say int star D equals malloc. Has something there. Well, I create this variable D, and when I call malloc, it gives me the address to a block of memory, right? Because it's, say, for example, A0C. And so that is my block of memory for storing those ints. AA0C. I want to get AA0C into here so P can work with it. So how do I do that? Well, what I'm trying to do is store AA0C at this address. So I need that address, which means on this end, I need something that stores the address of a pointer to an int. So I need int star star, and we'll say it's D here. Okay, so I need that. But malloc is returning, technically it's void star, but I want to treat it as an int star because that's what ultimately P stores. So how do I do that? Well, I'm going to write star D. So if you haven't watched my video in which I talk about pointers, and so I can't remember if it's the first video on pointers, I think it is, but it may be one of the ones about arrays or pointers, I show you a little trick. So imagine I declare this variable, int star star star, and we'll call this G. And I only put 3 stars here so I can give you more examples. So there's a trick to this. When I type, or excuse me, the variable type that we see, or that we have when I write, These are the column labels. Basically what I'm going to do is I'm going to think about drawing a line between different parts of this. So if I do this right here, then what I have is over here, I have int, star, 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 and on the right hand side I have G. So what that means is that if in my code I use G with no stars, its type is int star star star, a pointer to a pointer to a pointer to an int. If I write star G, what I left on the left, or what remains on the left, is int star star. So star G is of type int star star, because I still have int star 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 G. That's all this. When I have only int star on the left, what's on the right is star star G. Meaning if in my code I use star star G, its type is int star. And then finally, I can draw the final line here. And that gives me this. Int star 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 G. If I put all three stars on G, then the type of thing I'm dealing with is an int. So we need to think of that here. Even though D was of type int star, so really what I wrote was this. I wrote int star star D equals, because I passed it the address of P. And remember, P is of type int star, so this stores the address of a pointer to an int. When I write star D, what's left? Int star. Its type is int star, which matches P. So let's write code to do that, to demonstrate to you it really does work. So what do I need here? We're going to get this. The rest of this should be fine. I need 2 stars. So now star D will be that. And really, every place I write star D, it's really the equivalent of the P down here. So let's put those values in there. Actually, this will be, so this is not correct, so I need to change this. So what does that need to be? What it really needs to be, I need to dereference this. I'll explain that here in a moment, but let's see if that works. It compiles, that's a good sign. There's my numbers. So what's happening here? Well, remember, I just got through saying that int star is of type, star D is of type int star. So really, for all intents and purposes, everywhere I write this, it's the same as writing P down below. So if I want to use P sub I, then I write star D sub I. If you don't know the difference between pointer notation and subscript notation, you should review the video I did in which I talked about pointers and arrays and the relationship. But this right here, well, let's start with this one right here for P. P sub I is equivalent, so this is subscript notation. This is equivalent to writing P plus an offset of I, where the offset is really using pointer arithmetic, dereferenced. So when I write this right here, and actually I think well, probably need the parentheses here, but it's sort of the equivalent of this. So it's really doing this, star D plus I dereferenced. And so you could even take this and say this is really just, well, we would have to change some stuff up. I was about to tell you something wasn't right. But this is what this is. Just to confirm that, if we try taking out the parentheses, now it thinks D sub I is a pointer, and I'm dereferencing that pointer. So I don't know if this will work. I don't think it will. well, looks like, well, so it didn't. It did compile, but you notice I got a segmentation fault because it's incorrect syntax. If D sub I had been a pointer itself, so if I'd created an array of pointers instead of an array of ints, then this would dereference one of those pointers. But that's not what I want. I want this. And there it works. So sometimes you have to do stuff like this. So if you watched my original video on pointers and you were left wondering, well, why would anyone have 2 stars? There's an example right there. If you find videos like this helpful, well, then help me out by hitting the subscribe button, please.